Hello and welcome to Hello and welcome to College Physics. This is the OpenStax text presentation for Aquinas Physics without calculus. What I'm going to do here is I'm going to go through this presentation, go over the key main points, do a couple example problems. When I do example problems, I'm going to reference the text that you have exactly and walk you through what they do. So I'm going to go back and forth between the textbook and the presentation itself. That being said, let's begin. So the first thing I'm going to cover is kinematics. That's essentially motion. That's how to calculate motion, how to know where things are going to be after things happen. And motion is everything. Motion is throughout us all the time. Understanding how it works is the basics, essentially, of physics. And it is also a introduction to a lot of other topics that revolve around physics. Physics, again, a lot of it's how things move, how things behave. So knowing the math behind how things behave allows us to understand what's going to happen before we do it. And then we can do it, verify this is true, or if something's different, understand why. Again, it's all throughout us. And the main topic of this chapter is going to be your basic conversations of position, time, velocity, acceleration, right? Those are the big parts. Those are the factors in the equations that you need to understand to get what's going on. Example here, some people bicycling around, right? They are moving from place to place. They have a velocity, they have an acceleration. Technically, you can calculate all those things if you don't know all those variables. Here we have a teacher moving from one place to another, right? What's important about this image here is I want you to understand that most everything you do, at least at this level of physics, revolves around position graphs. Here we have a classic Cartesian coordinate system, an x, y, x on the horizontal, y on the vertical, right? 2D motion. Moving from there is defined based on the graph. So this person, like, technically doesn't exist in the graph, right? But we put this person in the graph to understand their motion in a way that you can extract numbers from. X naught, x0 down there, we're going to refer to that as the starting position. Naught is where you start, and then everything subsequent following that would be followed by a number, or in this case, an F for finish. So X naught starts at 1.5 meters. She starts her motion where she starts it, but we are calling that 1.5 meters because it's 1.5 meters away from the origin where X and Y meet. Again, I am emphasizing this because we're going to be discussing a lot about position, acceleration, velocity in this chapter. So knowing how they relate on a Cartesian coordinate system and why we do that is important. That's the Cartesian coordinate system is also how we can describe things as being negative. Here we have an example of someone who, as you can read from the text here, this gentleman was sitting at the front seat there, and he moved to the back of the airplane. So his position itself is actually negative displacement if we build the airplane on this XY coordinate system. We can say he started at X naught, which is 6 meters from the origin, and he ends at XF, which is 2 meters from the origin. So he moved negative 4 meters. 4 meters are subtracted from his displacement. And of course, it's worth noting here, this is because we are saying the X naught origin point is located behind the back of the plane for this example. If we were to flop the plane around, then he'd be moving in a positive direction. So it's all about where you set up your organization. And up here is the cartoon version, right? Down here is the physical version that you can draw on your piece of paper. I'm going to highly suggest if you can draw something, if you can write something down and process, do it. Even if you think you could do it in your head, write it down anyways, because you're going to run into problems later on in this class and in other ones that you can't do in your head mentally. Teaching yourself to write things down as you go is paramount in basically all science. So x naught starts there, moves 3 meters back, moves 2 meters forward, xf. Your total distance is left. And as we can see here on this Cartesian coordinate system on the right here, we're defining moving to the left, or in this case, moving to the west, as negative. Because, again, think about your grid system, right? Up and right are positive, down and left are negative. We can apply this to so many things. But so far, everything we've done is essentially like left-right, right? A important understanding to get from this initial kinematics conversation is that descriptions of things can have different layers to them. For example, here we have a jetliner that you can describe in terms of distance traveled, or you can describe in terms of where it's going. So this distance here moved left and right, and there's numbers associated with it. That's important. 3 meters, moving 3 kilometers, for example, tells you something, but it doesn't tell you everything. A scalar quantity is what we refer to when we talk about the number of something. The 3 kilometers there is the scalar quantity. The fact that it's negative and negative equals west, meaning you move 3 kilometers to the west, is what we call a vector. That is what happens when we have a direction and a scalar or a magnitude or a number involved with it. You kind of need both to know where you're going. If you ask me directions, I say, oh, it's 5 miles away. Okay, thanks. Can you give me something more? Oh, yeah, 5 miles to the east. Now I know where I'm going. Right? Here again, Cartesian coordinate system, the classic grid we all probably are accustomed to from high school or the math classes. And everything is described this way. Even things that are very slow, like snails, right? So this picture here, we have an example of many different changes in displacement. So that we talked about x naught and xf being your movement on the x coordinate system. That triangle there, we refer to that as a delta. That means change. Classically, subtraction or addition, something like that. So if something moves and we want to show that in mathematics, or something changes, we want to show that in mathematics, we tend to use a triangle and refer to that as a delta. So if I say delta xc, that's going to be that third middle line moving to the right a little bit. So that you know the wording. So we can start going through examples. Again, everything I'm going through here is in the textbook. So if you want to pause the video, go to the textbook, try to answer questions, come back. Whatever works best for you is okay. I'm not going to do every single example. I'm instead going to do a select few that I think are important. If it's beneficial for you to do every one of them, go ahead and do every one of them, right? That's how that game is played. Going back here, during a 30-minute round trip to the store, a total distance traveled of 6 kilometers. The average speed is 12 kilometers per hour. The displacement of the round trip is 0 since there's no net change in position. Thus, the average velocity is 0. That sentence is sort of a make sense in physics, doesn't make sense in real world sort of things, right? Average displacement, net displacement, net change in position is 0 because you're back at where you started, but you obviously traveled, right? Average velocity is 0 because we define velocity in terms of positives and negatives. And when you add a negative and a positive number together, right, they can cancel out. Plus 3, 3 minus 3 is 0, right? Doesn't mean the 3's didn't exist. It's just the math is somewhat less intuitive to reality, but still correct within the math. And these graphs kind of explain that conversation there, right? The top graph is position. So since the position is back at 0, according to the graph, we kind of all where we started, but you did move, hence the triangle, right? Same thing with velocity. You have a positive velocity, you have a negative velocity. Those cancel each other out mathematically, but you still moved. Just you moved positive direction one way, negative direction the other way. Right? Lots of examples in the real world that if you can think about them from a mathematical or a physics lens, you can understand how the math works and why it's beneficial. Right? just more examples. These tie in with the book, but I'm not going to spend all this time going over every example in the book. So that's why I'm skipping past a couple of these things. Again, check in the book for the example if you want, but it's all going over the same conversation here. You can have velocity in a direction and acceleration in the same or a different direction, and it's going to affect it. The top car is speeding up to the right. The bottom car is slowing down to the right. And then we can get, I think this is our first, almost there. Here we have examples from, well, things moving and things accelerating. Again, this is in the book. I believe the next question, the next question I actually go through here. But let's just skip back to this. If you want to pause at any point when you're doing this question in the book, go back. That's fine with me. Although this stuff's kind of straight from the book. So this right here is example 2.4, which is said here, calculated acceleration, a train speeding up. And the question is, you have a train here, right? This train is accelerating from rest at 30 kilometers per hour in the first 20 seconds of its motion. What is its average acceleration during this time? Something that I'm going to be a very big proponent of is writing everything down. You shouldn't assume you know something and will remember it throughout the course of whatever you're doing. If it's relevant information, you can go ahead and write it down. Here's an example of that. Notice we did a dot for V naught of 0, a final velocity of 30, so a long arrow in a direction. We're calling them both positive because we have an XY coordinate system over here. And then an acceleration that we do not know. I personally probably wouldn't draw the arrows unless I think it's relevant. And when we get to more dimensions than one, they become more relevant. But those numbers are super important. V naught equals 0 kilometers per hour. VF equals 30 kilometers per hour. A equals question mark. Writing that stuff down reminds you when you get to the equations, what you know and what you don't know and how you need to rearrange said equations. And that's what, of course, is written in the book as well. So to solve this, we have first identify our knowns, and then we find an equation that relates all the knowns together. In this example here, we know that acceleration is equal to the change in velocity divided by the change in time. The velocity changed by 30 kilometers per hour because, again, we can go back here, your initial velocity is 0, your final velocity is 30. That's a change in velocity. That's a delta V, right? You start at 0, you end at 30. You've changed by 30. So we calculate delta V as 30 kilometers per hour. Plug that in. Delta T is the same thing. You start at T0, you end at T20. So delta T is 20. Math it out. If you have issues with conversions, you need to, first of all, practice them. And these questions all have conversions, so they're good practice. And secondly, write them out big like I did here. Notice I wrote I didn't write, but the book wrote the units on the top and the bottom and proceeded to figure out ways to cancel all of them. So the question itself is 30 divided by 20, but the answer here is in meters per second, right? Kilometers per hour per second is not meters per second squared because we want an acceleration. So we need to convert kilometers to meters, and we need to convert hours to seconds, and we need to make a new second. We need to get rid of kilometers and hours, essentially. So that's what's going on here. If you struggle with what I'm talking about at line 215 there, let me know. I can walk up through this stuff more with you. I'm a big proponent of practicing to get it. There's not, sometimes there's little tricks and phrases for unit conversions. Writing them out long ways means you're never going to be wrong. So that's my suggestion to you. But at the end, we find out that if this train starts at rest and after 20 seconds is at 30 kilometers per hour, that means it accelerated at 0.417 meters per second squared. That's the math. So trains can go backwards, and it's the same math, just you have negative numbers, and you have negative acceleration based on your definition of to the right is positive, to the left is negative. but it's the same math. You just have to use negative numbers. All right. Oops. Kinetic equations can describe and predict motion of objects such as kayaks racing, right? If you've ever been, boating or kayaking or canoeing or something like that, it's a lot easier to go with the current than it is to go against the current. That's what we're talking about here. Right. All right. Again, I'm skipping some questions because I'm not going to go for every single question in the text. That kind of takes too long and defeats the point, but I will go to example 2.9 and move on from there. 6, 7. I think that's the next chapter. I'm also, as you can tell, not delineating the subsections here. I'm just proceeding forward. This video is meant to be a companion to reading the text and the other things I posted in the class. Use it that way, right? Don't expect everything in the class to be told to you by me. I will be there to help, but if you're not putting in the effort to learn this stuff, then you need to put in the effort to learn this stuff. Don't expect me to go through every possible thing that's going to happen in the class. And that's, that. I'm just explaining why I'm skipping questions and stuff like that. So what does this relate to? This question here. Calculating final velocity in an airplane slowing down after landing. An airplane lands with an initial velocity of 70 meters per second, then decelerates or has a negative acceleration of 1.5 meters per second squared for 40 seconds. What is its final velocity? So when we write everything down, we know it starts at 70 meters per second and decelerates, which means it accelerates in the opposite direction of velocity, or it slows down. These all mean the same thing. Mathematically, though, if the velocity is, we're going to call positive, slowing down means you're accelerating in the negative. So that's why we have a purple arrow going to the left and a negative sign on the 1.5 meters per second squared. We also have t equals 40 seconds. Useful, not written there, but useful. And then final velocity is the question mark. How fast is this thing going at the end? So again, identify our knowns, identify our unknown, VF, find an equation that has all these in it. The equations are shown in the textbook. I suggest maybe doing even a separate piece of paper that has all these things when you're going through the assignments. It's good to not have to try to look this stuff up, and it's pointless to try to memorize it. There's no need to. Just write it down. Right. We do have an equation that has acceleration, velocity, final velocity, and time in it. V equals V naught plus AT. In this case, V is going to be synonymous with VF. VF is what we want. So we plug in the information. We know it starts at 70 meters per second. And we know that the negative 1.5 times 40 is our acceleration or time, and we math it out. Be smarter than your calculator. Think about how you put in the information so that you don't screw something up and get an incorrect answer, right? At the end of this, we find out that the final velocity is 10 meters per second. So after 40 seconds, the airplane is decelerated from 70 meters per second to 10 meters per second. Plug and chug at this level, sort of, right? And that's again what's shown here. Slows down due to negative acceleration, reducing the velocity. That was a lot of things that sort of resulted in set known velocities and accelerations. We can keep adding more and more variables to the equation. The equations get more complicated, but the process is still the same. So here we have very quick accelerations from different levels. What do you do in those scenarios? What if I'm asking you something where t isn't equal to, well, t doesn't start at 0, right? What do you do then? Or what do you do when I'm asking you for a particular section of displacement? I'm asking for the acceleration only in that little subsection. You can all do those things. It involves a lot of the same conversations. Just you need to make sure to find the right equation. I'll go over a couple examples of that. Right. This is exactly what I'm talking about here. I can ask you for a location given acceleration or a velocity given an acceleration. Both of those are determinable. You just need to find the equations and knowns and the unknowns. Let's do example 2.12 for that. 11, and here we go, 12. So here's a summary of kinematic equations that could be of use. Again, notice as we get more complicated, you get more variables, you get more sections to it. You get squareds, you get subset parentheses. You can do this math. If you have issues with it, take your time, slow down, go in more steps. If you try to rush this stuff and you make a mistake, you probably shouldn't have been rushing this stuff, right? So, calculating displacement. How far does a car go when coming to a halt, when stopping? So you got on dry concrete. So we're skipping over extra variables like, friction and stuff like that. On dry concrete, a car can decelerate at 7 meters per second squared. So its negative acceleration is 7. Whereas a wet concrete, it can decelerate only at 5 meters per second squared. So there we go. Find the distance necessary to stop a moving car at 30 meters per second or 110 kilometers per hour on dry concrete and on wet concrete. Repeat both calculations. Find the displacement from the point where the driver sees the traffic light turning red, taking into account a reaction time of 0.5 seconds to get his foot on the brake. So the first question is kind of straightforward, just V naught to VF, except that V naught is 30 and VF is 0, as opposed to the previous ones where we started at 0. And then do that exact same conversation, but instead of not caring about the time as much, now you have a reaction time to take into account. So, first of all, of course, determine your knowns, right? You start at 30, so V naught is 30. You end at 0, so VF, or V, is 0. Your acceleration is negative because you're decelerating. So if you're asking about displacement, how long does it take to do something? That's an X, it's a location. So we are asking for delta X in this point, because how long does it take to stop? Knowing what all these letters mean in like real world wording is what's useful here. X minus X naught is a delta X. Change in placement is how long it takes to go, so how far away something is, right? So if we rearrange the equation here, the V squared equals V naught squared plus 2A delta X, we can rearrange the equation to solve for delta X, as shown here, and then do our math. Determining that it takes about 64.3 meters for the car to come to a complete stop on dry concrete, because we say X naught is 0 and X is the distance it traveled. Do the same thing on wet concrete. You simply replace the -7 with the -5 to get a longer number. So we have distances for dry and wet concrete. Now we are caring about time involved, given that initial, as written up here, reaction time of half a second. So what do we do there? Well, again, we find an equation that has what we want and we solve for it. So we know our knowns. We define equation, in this case, X equals X naught plus VT. And we can determine based on that how long you're going to be going post that reaction, given the velocity that we're talking about here, right? Your velocity is 30, your reaction time is half a second, and your reaction acceleration is 0 because you do not accelerate. You do not decelerate for that half a second. So if you're traveling 30 miles per hour in a half a second, you go 30 meters per second. In a half a second, you go 15 meters. So we use that. We add that to our braking distances from before to find out how long it actually would take to stop, given the human error of what we're talking about here. So if the pavement is wet, you need at least 100 meters to stop completely when you see something happen. So if you're tailgating, there's not enough space, right? This is what I'm talking about. By you add more equations, the math doesn't become harder, it just becomes longer. You just need to put the effort in. picture that we just got done talking about there, right? The following chapters on problem solving, it's kind of writing in words I've been talking about already. Write stuff down, take your time, check your work, stuff like that, right? So let's move on to gravity. Gravity is cool because it is a constant in physics. If you know gravity and you're not like caring too much about distance from the earth, right? In this class, you really won't. It is a known that you always plug in, and a lot of math in physics and other things really care about gravity because gravity is always affecting everything. Gravity we tend to define as a negative acceleration, negative 9.81, because unless you're wanting to go down, gravity is working against you, right? Here's a couple of graph examples of what gravity does. So all three of these are shooting something up in the air: position, velocity, and acceleration. And the interesting thing to point out here is that top graph, the position versus time, that's not the trajectory of the arrow. So the arrow is not going to the right. That's simply how high or low the thing is from when it was fired. So make sure you understand why graph 1 is not motion in the horizontal direction. And for that matter, graphs 2 and 3. Of course, if you drop down, you tend to want to still consider A to be negative. You have a velocity that is negative. So honestly, sometimes I don't think about it that way. If they're in the same direction, I both consider them positive. That's not necessarily good to do, but it's just kind of force a habit. Be better than your instructor. Keep acceleration negative. And there's the example I was talking about before. Throwing something up there versus it falling. The like little loop-de-loop on the graph there is not because the rock is moving away from him. It's just to better explain what's going on. Now, I'll do a math example. Here we go. So you can see this in action. But again, falling objects. There we go. It was 216. Yes, 216. 15. There we go, 216. So again, if you care about this picture and the math behind it, it's right here. Go to your book, work through it. I'm working through selected questions. So finding G from data of a falling object. You can measure movement of something and you can measure time, therefore you can calculate velocity, but can you get gravity from everything that we measure? So if we, this other one's bigger, if we drop a ball and measure the displacement and the time it takes to measure that displacement, we can calculate velocity and we can graph all of these things out. Given this data, can we calculate how fast it's falling? And notice the time intervals as time increases, the distance between them also increases. So the distance between 0.1 and 0.2 seconds is smaller than the distance between 0.4 and 0.5 seconds. This is indicative of acceleration. So we can draw a sketch, kind of a pointless sketch, right? But is what it is. There we go. Classic slope stuff. I'm assuming at this point that you know what a line graph looks like, so I'm not going to go too deep into that. So how do we calculate these things? Well, we do every question the exact same way. What are my knowns? What are my equations? Can I solve what I need to solve with my knowns and my equations? In this case, I know where I start. Y equals negative, Y naught equals 0. That's a Y because we're doing horizontal motion instead of vertical motion. Wait, sorry, we're doing vertical motion instead of horizontal motion. If it was horizontal motion, I'd be using an X. It's vertical motion, I'm using a Y. And I know a time, I know a velocity that I start at, V naught equals 0. And I actually have an equation that solves for acceleration, gravity, that asks me Y naughts, T's, V naughts, all these things. So what I do is I take my equation. As said here, it substitutes in 0 for V naught to kind of get rid of that little center problem there, because V naught 0, anything times 0 is 0. Anything plus 0 is pointless. And then we can rearrange to solve for A and math. Again, I'm gonna keep on this. We have negatives, we have squareds, we have divisions. Be smarter than your calculator. Do the math slowly so you don't get an incorrect answer. We end up with, after we do our math correctly, an acceleration of negative 9.801 meters per second squared. 9.8 or 9.81 meters per second squared for gravity is something you're probably gonna, if you haven't memorized already, you're just going to, because so much math we do in this class is real world or real world analogous and cares about gravity. Okay, so now more examples, more questions from the text. There's a part here where, yeah, graphical analysis. I don't really go over the graphical analysis that much. It basically just ties in with the math. If you can do the math and you know how to read a graph, you can do the graph. It's the trigonometry sort of thing, right? But everything keeps lining up at the end. So there you go. That's chapter 2. If you got questions, shoot me an email. I'll comment them down below. I check these comments not infrequently. So to reemphasize my main points here, what are your knowns? What are your equations? Do you math slowly and correctly? And connect the equations with what you're doing, right? Why is acceleration negative? Well, because I'm considering up positive, therefore, if I'm going down, it's negative. Make those real world connections. As the class and further classes beyond this get more difficult, understanding what you're doing and how it's more than just numbers on a piece of paper is going to be crucial. So thanks for watching. Take care.